Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Turned out of the banking bombshell causing shockwaves around the world.
Good morning, good afternoon, good evening around the world, and welcome to Nodes 2020. My name is Emil Ephraim, and I'm one of the co-founders and the CEO of Neo4j. And I'm going to be your host for the next hour or so as we kick off Nodes 2020. I think we have an absolutely amazing 10 hours ahead of us, so let's get started. I'm really excited that Nodes is happening again. It's been almost exactly a year since we last had our first huge online virtual conference, Node 2019. And of course, it is bigger and better already than last year. We have over 10,000 people registered to attend and watch over 70 talks by close to 90 speakers. And it's all moderated by over 30 community partners from a wide variety of backgrounds, cultures all over the world, a wide, discrete range of technologies who help us spread both the love of graphs and the word of graphs and attract a larger and much more diverse audience. So thanks everyone for chiming in and making this an amazing event. In addition to that, our sponsors made this event possible, so please make sure you drop by their virtual booths. For those of you who used Big Marker before, you probably know that there's a specific feature where you can attend each and every one of the sponsors' different booths. It's like a separate stream just for that sponsor. So please drop by and say hi, learn about their technology, and you can win some cool prizes. There's also a lounge area, which is basically a big chat room for all of us attending the conference. Please participate there, try to connect virtually. It's obviously nowhere near as good as being able to do it in real life, but at Neo4j and in the graph world, we're all about relationships, so try to strike up those virtual relationships in that lounge area. Over the next 10 hours, I'm going to be there as much as possible, so please stop by and say hi. Cool. So before we get started, a few words about Neo4j, the company. Most of this will talk about Neo4j, the product, but I'll take a minute or two and just introduce the company. So we're Neo4j, the company behind Neo4j, the product, which of course is the leading graph database platform in the world. Today, there are over 400 global enterprise customers, which business rely on Neo4j every day. And every single month, there are over 100,000 developers who use Neo4j to build applications or explore and make sense of data. Neo4j and graph databases are today used absolutely horizontally across a wide variety of verticals and industries and use cases. And as you can see here on the slide, it's used by some of the biggest brands in the world. There's a wide range of use cases. You have a few of them here on this slide. At least 60 or so percent of the commercial use cases that we see of Neo4j fall within the top 6 use cases, but there's a long tail of use cases outside of these top 6 because graph technology is a fundamentally horizontal phenomenon. You can use Neo4j in a wide shape of form factors. You can use it on-prem. Just go to neo4j.com/download and download Neo4j Community and install it locally in your data center, on a cloud service. You can go to any of the cloud marketplaces and consume it in that form factor. Or, of course, you can use a database as a service, specifically in Neo4j Aura. There are a wide variety of ways that you can get access to Neo4j. So 2020 has, of course, been a tough year for all of us. I hope everyone here on this conference is doing well and that you have taken care of yourself and your loved ones. Here at Neo4j, we are fortunate to have a sustainable long-term focus. So we've used this opportunity to double down on product. That has been the key area where we've spent most of our calories over the past 12 months. So I'm excited to tell you about a few of those things that have been happening since Nodes 2019. First and foremost, let's talk about the database. We've launched Neo4j 4.0 and 4.1, and overall, the 4.x series is just mind-blowingly good. There's so much stuff in there to talk about at Nodes 2019. I think there was a 15 or maybe even 20-minute segment just touching on a few of the features in just one of those releases, 4.0. So it's very hard to pick out select areas to talk about, but let me highlight three of them. The first one is scalability. 4.x includes the multi-database feature, which has been one of the top 3 requested features of all time. So very excited about that. It also includes sharding through Neo4j Fabric, which of course gives this horizontal scale out both read and write load architecture that so many has talked about in the graph world. So very excited about that. The second big area is around security, where we introduced fine-grained role-based access control, which means that depending on your role, you can access certain properties or not access certain properties. It's down on that level of granularity, property level, both for reads and for writes. And then finally, like the third area that I want to highlight is around developer productivity, and specifically the reactive driver architecture that was introduced in the 4.x series. Broadly, the Neo4j 4 series has been adopted already so far in 2020 by our largest customers, and it's enabling new levels of robustness and scalability for applications built on Neo4j. So that's the first one. The second one, second but not least in any way, we launched Aura at Nodes 2019. That was before we had even unveiled the name. It was pre-announced to the attendees of Nodes 2019. And of course, it's our self-serve, fully automated, always on and always updated graph database as a service. It is a mind-blowing piece of technology that we're going to spend more time to talk about later in this session. And then the third one that I want to call out is that we launched GDSL, which is the Graph Data Science Library, which really rounds out our platforms for support for graph data science. That platform, as you can see here on this slide, has 3 components to it. The centerpiece is the Neo4j database, the native architecture for storing connected data, storing and querying connected data using Cypher. And then to the left in the slide, you see the GDSL, the Graph Data Science Library, with a rich set of graph algorithms. And then to the right, you see Bloom, which is used to visually explore your data and make sense of the graph in an optical visual way. Those 3 components form our platform for graph data science, and that's also an area that we're going to spend more time on later on in this call. Stepping outside of product, we've doubled down on developers in 2020, and there are several examples of this. I'm going to call out a few. The first one is that we've redesigned the Neo4j developer training, documentation, and knowledge base from scratch, which I hope will provide a much more seamless way to navigate on our web properties. We've improved the first use experience of both a Neo4j desktop and Neo4j browser by including a first use graph experience where it comes already provisioned and pre-installed with a small prototype graph to make it easier for you to get started. In the same spirit, we've improved onboarding and getting started experience in Aura. Which makes it a lot easier to get started. You can also easily export data from desktop or local installation of Neo4j and import it into Aura. And then last but not least, we made Bloom available completely for free for everyone, locally, using Neo4j desktop, on Aura, and on Sandbox, which you can access from neo4j.com. It launches a small little Neo4j instance completely in the cloud from neo4j.com. And in all of those form factors, you can use Bloom for free. Many of you may know that we have this initiative that we're very proud of and that we're spending a lot of time on called Graphs for Good. And that's the umbrella under which, for example, the Panama Papers happened, where we try to make Neo4j available for high impact activities and projects in the world completely for free. And the Panama Papers is a good example of that. There's today over 20 independent projects using Neo4j to find the cure for cancer. It's being used in diabetes research and a wide range of projects to further for the good of mankind. In the beginning of the pandemic, right, so in the earlier part of the year, there were a lot of countries and organizations and individuals that reached out to us, and they started to introduce COVID-related projects based on Neo4j. And they were things like scientific analysis, like COVID graph, ranging all the way to contact tracing for some countries, to fighting misinformation like Project Domino. And we've tried to support that as much as possible under the Graphs for Good initiative. And I'm super proud to see how the entire Neo4j community has risen to the challenge of this global pandemic and really come together and pulled up in all kinds of creative ways to try to use connected data to try to do our part in figuring out how to solve this, the COVID-19 pandemic. In the similar spirit of Graphs for Good, just last month, the ICIJ, which is the organization behind the Panama Papers, they published another investigation. And this time it's of suspicious financial transactions. They're called SAR filings or SAR filings, which total over $2 trillion US dollars, right? So that's pretty significant chunks of change that these journalists have analyzed and verified, and with a lot of data analysis tools like in Neo4j and Linkurious, and they basically built out an AML solution, an anti-money laundering solution to track how money is being trafficked from offshore accounts in one location all the way through the global banking system. It seems to me, looking at the news cycle, that this investigation is already overshadowed by all the other news that is going on in 2020. But we actually believe that this, on some level, is even more important than the Panama Papers. And if you find this interesting, you can already explore the published data in Neo4j. There's an online sandbox for that. So if you go to neo4j.com, you click on Sandbox, you can choose the FinCEN files data set, you get access to it, you can start playing around and see if you can uncover any patterns that haven't yet been written about in the press. So that concludes our year in review. It's been, of course, a tough year on many levels, but also a very exciting year in the Neo4j and broader graph community. And now we're on to Nodes 2020. We're going to start by looking forward to the future. In particular, since it's the year 2020, it's the beginning of a decade, I thought that it was appropriate to see that what do we believe is in store for the next 10 years in graphs. I believe that there are 4 major pillars that are going to shape how the graph database category will evolve in this decade. The first pillar is the shift to the cloud. The second one is putting developers at the center of everything that we do. The third pillar is the rise of the data scientist in general and specifically graph data science. And then finally, I believe this is the decade when the property graph model will realize its full potential. So let's have a look at each one of these pillars in order. And first of all, the shift to the cloud. So this should hardly come as a surprise to anyone listening in. Our industry is obviously part of this massive secular shift towards cloud delivery and consumption of software. A little bit more subtle is probably that this is actually happening at a different pace for each layer in the stack. It first happened to the infrastructure layer, specifically for VMs. If you recall, the first ever cloud service was EC2, Elastic Cloud Compute from Amazon. And that is really the VM layer of the stack. And then it also happened concurrently in the application layer of the stack. So think your Salesforce or your Gmail or your Hotmail, right? And actually the data layer of the stack, it took a while for it to happen there. It was held back for a variety of different reasons, primarily data gravity and then compliance and regulatory reasons. But nonetheless, it is very clearly happening right now. And it really hit an elbow, the shift of the cloud, of the database layer into the public cloud. It really hit an elbow in the curve in 2017 and in 2018. And it's only accelerating from here. So the question then is, why is this happening? I think there are 2 drivers why people want to consume databases through the public cloud. The first one is simplicity. Basically, you can focus on building amazing applications, not on managing infrastructure, right? The second one is elasticity. You can write your application and then your backend can grow and shrink automatically. And you pay only for what you need. If there's burst one day, it grows to that size, handles that load, and then it shrinks back down, and you paid only for that peak load during that one day or a couple of days or whatever it was. So I think those are the 2 big drivers. So let's review now what's happening in the world of cloud database services, specifically for the Neo4j community. First and foremost, we have Neo4j Aura Professional. We mentioned this already. It was launched at this conference, Nodes 2019, exactly a year ago. It's a fully managed, fully automated, completely self-serve, always up to date, always on graph database service. It's been up and running now successfully for an entire year, hundreds of customers, and it's actually handling over 2 billion queries per month, which is a pretty staggering number. In fact, just a few weeks ago, there's actually a particular week where there was over 1.2 billion queries in that week. And if you just spread that out evenly, that's actually over 2,000 requests per second. But of course, that's not actually how it happens. It will actually follow most likely a Poisson distribution, for those of you who remember your statistics classes from college. So it's actually even more a sustained rate of more than 2,000 queries per second. Neo4j Aura is a rock-solid product, and it's super easy to get started, 9 cents an hour. It will scale up to support your development and your production needs. So for those of you who are curious, I highly encourage you to check it out today. There's a link at the bottom of this slide. I think it will be concurrently posted into the lounge area chat room, so you don't have to sit here and try to transcribe it off of big marker visually. So you can just go click there and sign up today. The second of all, we launched Neo4j Aura Professional on GCP, on the Google Cloud Platform. And we're really excited about our deep and strategic partnership with Google, which, as some of you will recall, was announced in early 2019 at the Google Next conference. And Aura on GCP is already available in 8 regions around the world. It's integrated with the GCP marketplace, so you can pay with your GCP credits or your pre-committed spend, and the pay-as-you-go pricing is predictable. If you find this interesting, there's an equivalent link at the bottom of the slide, so please sign up to that. Hopefully it's going to be posted in the Big Marker Lounge area right now as well. And then finally, we heard loud and clear in this year that a fully managed Neo4j in the cloud is exactly what you want. But on the flip side, there are certain requirements that the world's largest organizations have, such as security integrations, be it maybe with Active Directory or Kerberos, compliance like maybe SOC compliance or HIPAA compliance. And we've worked very closely with a handful of large enterprises to build that into a new cloud offering. And that's Neo4j Aura Enterprise. And we're launching it in early 2021 on GCP and AWS. And then Azure is going to follow later on in 2021. If you find this interesting, stay tuned, pay attention to your neo4j.com, and you're going to be able to find out more. So in summary, in this decade, on-prem will still remain important, and hybrid cloud deployments will remain important, and in particular, your local desktop environment will for sure remain important for that rapid iteration in a local environment as you build your applications or you're trying out your machine learning models. So that's all going to remain important, but Neo4j throughout this decade is going to shift into a cloud-first company. So that's the first pillar. On to the second pillar, putting the developer at the center of everything that we do. So if we take a step back, broadly speaking, there are two ways of growing a product company like Neo4j. One is top-down, where you walk into the executive office, either the CIO for infrastructure technology like us, or into a line of business executive with beautiful PowerPoint slides, and you blow them away with just how amazing your product is in those slides. You sell it to that CIO or that line of business executive, and then they push it down into their organization. That's top down, right? Or you can go bottom up, where you build a product that is so amazing that the actual people, the practitioners who use it on an everyday basis, they might be the support desk people, right? If it's that type of a software, or if it's a CRM, it might be the salespeople. And of course, for a database, it's developers, right? You build an amazing product that the people who use it every day, that they love, and then they bring it into their organization, they tell their management, and then that's how you grow and become adopted inside of these big companies. And I'm not going to argue that either one of these is the better approach to building a company. But for me, the one that makes sense to me is the bottom-up approach. And there are two reasons why I find this one particularly enticing. And the first one is actually ethical, and I take a very kind of simplified, pseudo-utilitarian view of this. And the way that I think about it is that imagine that the world is a video game, which, by the way, it may actually be, and that everyone that walk around on this planet have a happiness-o-meter, on top of their head, right? Look at Link here from Zelda on the slide. And every interaction that people have with my company, either with the product, with the people inside of Neo4j, that happiness-o-meter is either going to go up or it is going to go down. And the way that I think about it in a very simplified manner is that when I go to bed every day, I want the sum of those happiness-o-meters to be positive, right? And if you think about these two approaches, if you do the top-down approach, the CIO or the executive is going to be very happy because it checked all the boxes that they need, and they're one person. But the tens of people or hundreds of people or sometimes thousands of people in that organization that use it on an everyday basis, the software is not built for them. It was built to sell into the executive, right? Which means that the usability can be good, but most frequently it sucks, right? And if you add that all up, that's a really negative impact on the world, right? If you flip it to the bottom-up one, you have to build a product that makes all those tens or hundreds of thousands of daily practitioners to make them happy, right? Otherwise, they won't adopt it. Which then leads to the next reason why I like the bottom-up one, right? In both of these approaches, it is easier, it's better if you have a good product, right? But with the bottom-up approach, it requires that you build great products. It just won't work without that. It requires you to have a product that the people actually use it, that they love. And for a database, that means building a product that developers love. So the question then is, how do we do that, right? And this is an area that we've spent a lot of time thinking about here at Neo4j, because it's very central to how we operate. And I believe that it all starts with a mindset. And here's how we think about every feature that we build at Neo4j. We look at what developer expectations are. We look for what's most missing, the most critical gaps. So for example, back in the days, we had Cypher, right? We had just invented Cypher. Prior to that, it was just an embedded Java API, and people loved Cypher. But you could only embed it in your programming language in drivers. And wouldn't it be great if you could just execute Cypher interactively from your web browser? Well, at that time, that was impossible, right? There was no way to do that. This impossible, we call that ground zero in our usability hierarchy. It's not even possible to do something, right? And the first step then is to make it possible, right? And in order to solve this problem for us and make it possible, we created Neo4j browser, right? And most of you on this call have probably used Neo4j browser. Probably all of you who have ever used Neo4j, you used Neo4j browser. But possible is of course not sufficient, right? We want to also make it usable. We want to make it consistent inside of Neo4j, reliable so that it works the same way over and over again. And for Neo4j browser, we want to send a query and get a result back. That's very nice. But you also want to actually make it usable so that you can save your work, you can come back later and pick up where you left off and keep working on your queries. So that's what we meant with usable, right? So that's very great and that's useful. But it's even better if it's also consistent with all of your other daily developer tools, right? If we don't just make it useful, but we make it normal, right? So for your Cypher queries, that means that you can not just save and load them from your browser cache, which is how it initially was with browser. You should also be able to save and load them from your local file system, right? So it can be picked up by all your other tools. You can check it into GitHub, you can open it up with your IDE, and so on and so forth, right? So that's amazing, I think, but we don't want to stop there. We also want to ultimately make it magical. We want to turn it into an experience where it's this invisible force multiplier, where it's such a pleasant experience that you want to come back. Like you don't need to go back to it, you want to come back to it, where the technology itself really disappears, it diffuses into the background, and where the mechanism of how the technology works is hidden, right? It's like clockwork inside of a watch. We, Neo4j Inc., the producers of the database, like we worry about how to make things work so that you, the users of the product, can go back to worrying about what you want to do. And I believe that when technology fades into the background, that allows you to get into the zone, right? Into the state of flow and hyper-focus on the problem at hand, right? And we're not there yet for everything that we build, but we're not going to stop until we are. So that's the second pillar. Now on to the third pillar that I believe will shape this decade of graphs. I talked a lot about developers in the previous pillar, but data scientists are an equally important constituent for us here at Neo4j. In this decade, we will see the rise of data scientists in general and graph data science in particular. Gartner recently said, and this to me is a quite extraordinary quote, "Finding relationships in combinations of diverse data using graph techniques at scale will form the foundation of modern data and modern analytics." Just think about that. If your manager or your manager's manager ever doubt the wisdom of you investing in and investigating into graphs, then just show them this quote. It's the foundation for modern data. It's the foundation for modern analytics, as per Gartner. A few months after they released that statement in the report, they issued a separate report where they'd surveyed companies globally for existing or planned usage of various AI and machine learning techniques. And a mind-blowing 92% said that they plan to deploy graph techniques within 5 years. And there's also a surge of academic research focused on this right now, where there's been over 28,000 peer-reviewed scientific publications about graph data science in recent years. And that pace is accelerating. If you chart it out, it's a very clear exponential curve, where the entire research community around machine learning has this as one of their top areas of focus in order to advance the field of AI and machine learning. Graph data science actually has a long and storied past, and I'm not going to go through it all in detail. It goes all the way back to the 1700s and Leonhard Euler, which of course invented graph theory as a discipline of mathematics, ranging all the way up until when Google used PageRank, which really was the first time that it got used at scale in the software industry or in the internet industry. Neo4j, of course, here we invented the modern graph database in the mid-2000s. And then fast forward to today, I think we've made some significant strides in terms of advancing the state of the art of graph data science for the enterprise. And here to tell us more about that is none other than Alicia Frame, who is the lead product manager here at Neo4j for data science. So over to Alicia to tell us more about this.
Awesome. Thank you for that great introduction, Emil. And so Emil has brought us from the 1700s to GDS 1.0 and talking about the rise of the data scientist. And I'm going to talk about what we've been doing from 1.0 to today, so the last 4 months. And I'm really excited about the title of this section, the rise of the graph data scientist. I joined Neo about 18 months ago to build a data science product. And I think the funniest thing was when I joined, everyone said to me, at our in-person events in the before times, all of a sudden half the people there were data scientists and we don't understand why. And the thing is, data scientists know graph. We know it's useful. We know it's super cool. We just didn't have a way to do it at scale. And I joined Neo to really build an enterprise library to do graph data science. So I'm super excited about the progress we've made. So I kind of like to level set when I present on this. We hear data science, deep learning, AI. Those terms mean different things to different people. So whenever I talk about graph data science, I like to start off with definitions. What do I mean when I say we're doing graph data science? So when I think of data science, I think of answering questions with data. When I think of graph data science, what I mean is I want to answer questions not just with my data points, but with the relationships between them. And there's kind of a toolbox of different things you can do, right? So this Venn diagram shows kind of the universe of approaches in graph data science. So we have graph queries. This is your Cypher queries. I have my connected data stored in a graph. I have questions I want to answer. Show me how many accounts are there that have committed fraud 3 hops out from this node of interest, right? I know what I'm looking for. I can write a query. I can find that pattern in my graph. On top of that, we have graph algorithms in our toolbox. What this is different unsupervised and supervised machine learning techniques that can look at that graph holistically. And instead of finding local patterns, find global trends. Basically identify important features of the structure of your network and add new data to your data set. So that's figuring out which nodes are most important with PageRank, or doing something like community detection and figuring out which parts of the graph are more connected to each other versus the rest of the graph. And so we go from pattern matching to with queries to algorithms to find these global trends. And then uniting these is, how do I explain what I've done to someone who's not a data scientist? How do I explore what I've done interactively? And we have graph visualization. So just like most data scientists know, Matplotlib, Seaborn, Bokeh, inside and out, Neo4j offers tools for graph visualization, things like Bloom, so that you can interact with that and say, does this make sense? What have I found? Why? And communicate the value to your team. And you can kind of put these together to do everything from analytics, where you're just answering a question with graph data, I have a whole bunch of customers. I want to segment them into different user groups. I'm going to run Louvain. Or you can layer those algorithms together, those embedding techniques, and generate features for traditional model building in your kind of standard machine learning setting. And then visualization wraps it all together. But really, when we talk about graph data science, it's just extracting knowledge from the relationships between your data points to make better decisions. And one thing I like to make sure that we address upfront is, why are we doing graph data science? This isn't just me or Emil or Neo4j inventing a new use of the graph database, right? The idea with graph data science is it lets you make better, more accurate predictions with the data you already have. So, I've been a professional data scientist for most of my career. One of the things data scientists always say is, if I could just get a little bit more data, I could make better predictions. But the truth is, you already have more data, you're just not using it. So if you think about your data in your Pandas data frame, your Excel spreadsheet, you've got rows and columns, you have data points, you have descriptors. But in the real world, there are relationships between those data points, right? Maybe we're talking about fraud and you have individuals making transactions with each other. There are relationships there. Maybe we're talking about drug discovery and you have genes and chemicals and diseases, and there are relationships between those data points. So when we talk about graph data science, what we're doing is we're bringing those relationships to the forefront, and we're using queries, algorithms, and embeddings to reason about them and bringing that into our machine learning pipeline. So I'm not saying throw out everything you've done. I'm saying that you can make it better with graph-based features. So the idea is you load your data, your connected data, into a graph. You extract graph-based features, things like betweenness centrality, communities, page rank, and then you can bring that back to your tabular data world as new columns in your spreadsheet or in your data frame that you're making predictions from. And when relationships are important, what you'll find is that those relationship-based features you've created improve your predictive accuracy. They help you make better, more accurate predictions because you understand these global patterns, this extended topology of your network. And so the reason we want you to do graph data science isn't just because Neo4j is cool, it's because graphs help you make better predictions. So Emil hit on this one earlier in the deck, and I like to kind of circle back on what does Neo4j do for data scientists. I joined Neo to build a product specifically for data scientists. I've been using Neo4j for maybe the last decade, on and off. And at the heart of it is the graph database, right? Neo4j was invented as the labeled property graph. We give you native graph creation and persistence. You store your graph-shaped data in a graph database where you can understand, store, query those relationships. What we've built over the last couple of years, though, is the tooling for data scientists beyond just data storage. So we have the Graph Data Science Library, which is what I work on, which is kind of our scalable graph algorithms and analytics workspace. It's a library that works with your database to reshape your data and let you run queries and algorithms. At the other end of the spectrum, we have Neo4j Bloom, which lets you do that visual graph exploration and prototyping. And if you think back to that Venn diagram a few slides ago, right, we have queries with the database, algorithms with the library, and visualization with Bloom. So we now provide the full toolbox to do graph data science. I said earlier, what I work on is the Graph Data Science Library. I think it's super cool. What we've done here is this is the plugin for the database that lets you do graph data science at scale. So when we talk about the library, the first thing most people think of are the algorithms. There are over 50 algorithms in the library, as well as other machine learning techniques. And we kind of break these down into 6 categories. We have pathfinding and search. So is there a route between node A and node B in my graph? What's the best route? What's the cheapest route? Kind of standard graph operations that you're probably familiar with. We have the centrality algorithms, which say what's important, which node in my graph has the highest page rank, has the highest centrality score. We have community detection, which helps you break your graph down into connected subgraphs. So if you've done k-means clustering before on your tabular data, you might think about doing label propagation on your connected data. We have link prediction that tells you where there should be an edge that you haven't seen one before. We want to predict where they're missing relationships in our database. We have the similarity algorithms, which allow you to say, given two nodes, measure how similar they are based on their neighbors, their properties, their relationships. And then finally, in what we're bringing to you in this release is graph embeddings. And these are super exciting. I sometimes call them one algorithm to rule them all. But what they do is they are a class of machine learning techniques that learn from the structure of your graph to make predictions to solve your problem. And they generate unique representations of each node that you can use for feature engineering. And I'll demo this later on. But the secret sauce that's maybe less front of mind to most people is actually the analytics workspace. So we talk about Neo4j, the database, storing all of your transactional data. When you want to do data science, maybe you don't want to run it on the full graph. Maybe you want to run it on a different shape of graph than you've got loaded. What you can do is you can use the analytics workspace, the graph loaders, to subset, reshape, layer that underlying kitchen sink graph where all your data is stored into the right slice and the right shape for the problem you're trying to reason about. So the reason I'm talking to you all today is because we're super excited to bring you GDS 1.4, the fourth release since April of our graph data science library. And what's in here is pretty amazing. So I mentioned graph embeddings, the one algorithm to rule them all. What these are is they let you use matrix math and neural networks to learn about the structure of your graph. So a lot of people have heard terms like graph convolutional neural networks, graph native learning. In GDS 1.4, we offer 3 techniques to let you actually do graph native learning at scale. To make this possible, we also have introduced the concept of the model catalog. And what this is when you train a model, we persist that model so that you can apply it to your data. So I train a graph convolutional neural network to learn a representation of my graph that I can use for feature engineering. And then I have that trained model that I can apply to my data as I get in new data or as I reshape my graph so that I can fit my predictive models within the database. Embeddings on their own aren't super informative. They are a bunch of numbers. They're machine readable. They're not human readable. So we've also added machine learning algorithms like k-nearest neighbors to let you leverage those embeddings once you've calculated them, once you've trained your model, predicted your embeddings, then you can use things like k-nearest neighbors in the graph to build up more information, to make discoveries and predictions about the patterns that belong in your graph. And then the fourth piece that we want to highlight is one thing that's come up since we've released the database is, hey, wouldn't it be cool if I could write my own algorithm? Or I really like what you've done here, but I want to change it in this way. Or I want to leverage the model catalog. I want to leverage the graph catalog, but I want to make it a little different. So in 1.4, we have the Pregel API that lets you build your own algorithms leveraging our infrastructure. So our super scalable in-memory graph, our model catalog, our APIs. You can use all of that with our Pregel API that lets you just kind of put building blocks together to build custom code. And so with that, this wouldn't be a developer summit without a live demo. So what I have loaded up is in Neo4j browser, basically a retail graph that I use for a lot of different demos. It's pretty easy to understand. The first thing I'm going to do is just call up the schema so you can see what I'm talking about. So what I've got loaded into my Neo4j database is I have items that belong in categories. They're purchased by customers in transactions. And the customers are from different countries. And I use this graph because it's easy to understand. We all have made purchases before. And so what I want to do is I want to demonstrate using GraphSage and graph embeddings to, first of all, learn the structure of the graph, predict that embedding, and then build a nearest neighbors graph. So the first thing I have to do is I want to go in and I want to load in the data that I'm interested in. So in order to do that, I'm going to go ahead, and I talked about that analytics workspace. I'm going to create an in-memory graph containing just items because I want to create an items embedding. And I'm going to tell it to load in some information about those items. I'm going to load in price, the number of items sold, the stock code, the page rank of each item, and the category that it belongs in. And for relationships, I'm going to load in a similar relationship that I created before this demo based on co-purchasing. So these items were bought together. And this is what I'm going to load into memory to train my graph embedding on. So I'm just going to click run. Super fast, I've got my in-memory graph. Now I'm going to train GraphSage. And when we talked about GraphSage, that was that convolutional neural network where we sample data from the graph, we aggregate information about neighbors, then we learn a function that can make predictions for your embeddings. So all I'm going to do is just call the name of the technique, and I'm going to tell it to create a new model called GraphSage Demo, since this is a demo. I'm going to tell it, in addition to using the items graph that I loaded, that it can use a bunch of properties that I've loaded in: category, sold, price, stock code. And there's some hyperparameters that I can tune, basically telling it, how do you learn the structure of these items? And so I'm going to go ahead, and now that the code is there, I'm going to run it. And what this is doing is it's training a GraphSage model. And so you can see right here, I've got GraphSage Demo, and it's a GraphSage model. And I can see all the configuration about that model that I just trained. And so what it did is it stores this information in my model catalog. And so the model catalog is where I store all the different models that I've trained so I can use them to apply to my graph. So now I can see that I've got a GraphSage model, and now I want to use it. So the first thing I want to do is to show you all, if you're not familiar with embeddings, what do those look like? And so I'm going to just stream the results. And graph embeddings are really powerful, but they're machine readable. What they are is I've trained a deep learning model to learn the structure of each node as a bunch of numbers that uniquely represents each node and can be used to predict these nodes are close together in the graph, these nodes are far away, these nodes are structurally similar, right? You can think of it like super powerful feature engineering. But to a person, it just looks like a whole bunch of numbers. So every node in the graph gets this embedding. Super cool. Not useful. So what I want to do is save that to my database. So I'm just going to write the results back and go ahead, store that information. And once those properties have been written back, they're available for me to use for other algorithms. So I'm going to go ahead and I'm going to build a nearest neighbors graph using the new embedding property that I just wrote back. I'm going to create a new relationship that tells me which items are most similar to each other based on their embeddings. I'm going to kick that off to run. And so what I've done is I've gone from raw data, trained my GraphSage model, applied it to my graph, and then used the output of my GraphSage model to construct a k-nearest neighbors graph. Now to kind of finish off that Venn diagram, I'm going to go over to Bloom to visualize what I've done. And so I've got Neo4j Bloom open in my browser, and I've stored a few search terms ahead of time. And so the first thing I want to do is I want to find a node where it has nodes that are similar to it in the co-purchasing graph, that base graph I started with, as well as nodes that are similar to it in my embedding similarity, where there's not overlap. So it has some nodes that are similar based on co-purchasing, some nodes that are similar based on the embeddings, but those are different nodes. And maybe that'll make a little more sense when I pull that up and run it. So I'm going to have similar embeddings. And this is going to pull up an example of that data, and it'll load in just a second. And what I can see here is I'm using Bloom's new hierarchical layout, so it's pretty easy to look at. And I can see my red spot gift bag. This is that central item where I'm looking at what's similar and what's dissimilar. On the top, I can see the items that are similar based on co-purchasing. So these items were bought together. This is that base graph I loaded in to do my training. And at the bottom with the orange relationships, I see the items that were found to be similar based on their graph embeddings. So the topology of the graph for these nodes looks similar to the gift bag, whereas these nodes up here were just bought with the gift bag. And if I just kind of take a look at what I see in Bloom, I can see, well, it looks like the gift bag was co-purchased with a lot of other, I don't know, wrapping paper, gift wrap items. Whereas on the bottom, it seems like I've got a much broader kind of cross-section of items. So what I'm going to do is I'm going to go in and I want to add the categories that these items belong in. So I'm going to use a new search phrase in Bloom. And what this is going to add in for me is it's going to link these items to the categories that they belong in. And so this will take just 1 second to pull back. And what we can see is it zoomed out to get everything into frame. But my intuition on the co-purchased items was right? They're all seasonal. But if we look at the similar embeddings, what we see here is these belong to a bunch of different categories. We've got quite a few in home decor, we've got bathroom, we've got garden. So what I can see just from this super quick, 5-10 minute demo is the embeddings are learning something different than the co-purchasing graph. The embeddings are learning topologically, my red spot gift bag looks like my vanilla candles. Maybe that's because we're buying candles to put in gift bags. Maybe it's because both of those are items that get added on to larger purchases. But I'm able to unveil new information from my graph and using the embeddings and then reason about it with Bloom. So let's go back to the slides. So putting this all together, hopefully what you guys have seen is we started from pointers, right? We have queries to answer questions with connected data. In my example, you could think of it as when I created that item graph that I loaded into memory. Then we can use patterns. We can use graph algorithms to uncover trends and patterns in our data. We can start reasoning about this is in this cluster, this is in another cluster. And then what we've introduced in 1.4 is the ability to make predictions. So if you think of this as like the road to, the rise of graph data science, what we're bringing you now is graph native machine learning to learn the topology of your graph to uncover new facts. And if you think about bringing this back to the hierarchy of needs, this is really kind of when we get to that awesome level, right? Going from possible to pleasurable to amazing. For me, predictions are pretty amazing. Just to wrap up, if you guys are curious about any of this, we have other talks at Nodes. You should totally check them out, including a deep dive into GraphSage. We have developer guides, and we also have books that you guys can download for free to learn more. And with that, I'm going to hand it back to Emil to talk about the future of the property graph. So thank you so much for your time.
Thank you, Alicia. That was fantastic. I am so excited to see what graph data science can do to the world of AI and machine learning as this decade is unfolding. So that was the third pillar, and now on to the last of the four pillars, which is the property graph model. And I believe this is the decade when the property graph model will truly live up to its full potential. Before we talk about that, though, I thought we'd take a little bit of a step back and look at what we've collectively achieved in the last decade. If you recall, we walked into the last decade with NoSQL just having formed, right? So NoSQL as a term was coined in 2009. We loved that. We saw that as a movement of non-relational databases that rejected the notion that you should put all data into one singular type of database. And it recognized that we entered into a world of plurality, of polyglot backends. And we really agreed with that. We rejected it as a product category. We felt that these were not interchangeable products, but we worked really hard to establish graph databases as a distinct category in the broader umbrella of innovation in data. And it worked really well. If you look at this chart here, you'll see this is from a site called DB Engines. I'm sure many of you are familiar with it. It measures a number of signals around buzz and awareness of a certain databases. So for example, number of Google searches, number of Twitter mentions, number of job posts, number of skills on LinkedIn, and so on and so forth. And it computes a score. But it does that per individual database, but even more interestingly, per database category. And as you can see here, for most of the last decade, graph databases was the fastest growing category in all of data, right? And we started out, we coined the term graph database, and so initially we were the only one, right? Now, I just looked yesterday, there are 31 other graph databases, a total of 32 graph databases tracked by DB Engines. So there's this amazing choice of different types of graph databases, which truly makes it into a real category, not just a one-off thing. So that's fantastic. And if you look at then where the depth of adoption is for graph databases and what we truly achieved in the last decade, you can zoom in and you see a number of sweet spot use cases, right? These are the ones that we actually talked about at the beginning of this session, right? We talk about personalization, real-time recommendations, master data management, and so on and so forth. And what they all have in common is that they're operating on connected data, but in particular, they have low latency read requirements on multiple hops of data operations, right? So that's kind of the joint thing between all of these use cases. And this, of course, is a situation where a graph database have orders of magnitude better performance compared to a relational database or really any other data model out there. So that's collectively what we achieved, us here at Neo4j, for sure, you here on this call, the broader Neo4j and graph community, alongside with all the other graph vendors as well in the previous decade. Taking a little bit of a step back from that and a little bit of a detour, and then I'll turn it back into the property graph model. When you look at most domain models out there, my belief is actually that for most applications out there, most domain models are actually inherently connected. Just for fun, I looked up the term domain model on Wikipedia, and lo and behold, there was an example of a domain model, which you can see on this slide. It seems to be from a US healthcare model, and you can look at that. It is very, very connected, right? It has a bunch of boxes, providers, healthcare supplier, and so on and so forth, and they're all connected in various ways. I also went to Google and did an image search for domain model in an incognito Google Chrome window and ended up with this page, right? Which is just a page full of domain models. Every single one of them is highly connected, as you can see. And I bet that if you think back on all, or at least most of the applications that you built in the past 5, 10, 15, 20 years, you're going to look at those domain models and you're going to realize that, wait, they actually look like the ones in this slide. They're connected. And so let's take a little bit of a look at that domain model from Wikipedia, the US healthcare one. We can take that domain model and we can store it in a relational database, no problem. Like, we know this game. We've done this before. Third normal form, ER modeling, like you name it. Basically, wherever there's line in that domain model, we break it out into foreign keys, possibly join tables depending on the cardinality. We know how to fit this, right? Some of those domain objects will end up in one table, some in multiple tables. It's doable. It's a little bit awkward. It takes some time, but as an industry, we know how to do it. We've worked through this many, many times before. We can also model it in a document model, right? And here it's actually easier to represent some of the stuff than in the relational model, which is one of the reasons why, not the only, but one of the reasons why the document database model has been so popular in recent years. But actually, the connections between all these various entities are even harder to model than in the relational database. You have to encode them into your document. You have to say that, you know, this provider over here is called ID 123, and if it's connected to this individual over here somehow, then you have to have a value. Remember that it's 123, and if this one gets deleted, there's no automatic way of maintaining that referential integrity. So it's actually weaker at maintaining those links in all of those domain models that we saw before. And so then we move over to the property graph model, and it's the most natural fit for this domain. Because exactly like all the domains on the Google image search slide, it's a connected data model. So it fits hand in glove with the property graph model. There's no transformation needed. Every single element in that domain model can be directly represented in the property graph model. It's the best fit of all the data models that I know of for most applications. And I'm not saying that you can't represent this domain model in the other data models. We just walked through how to do that in the relational model or in the document model. These data models are all isomorphic, which is a fancy way of saying that you can transform data from one model to the other without loss of data, right? So it's not interesting to figure out, can you store this data in one of the models? You can in all of these models. They are the equivalent of Turing complete, but for data. The interesting thing, is it a good fit? Does it fit hand in glove, right? And I'm not also arguing that this is necessarily true of the software that these products are trapped in today, right? In some cases, even if you have a highly connected small domain model, It's actually easier to put it in a relational database today, right? Because there's just more mature tooling around and so on and so forth. But if you look purely at the data model, and then if you break down that domain model into its atoms, they can all be one-to-one represented in the property graph model without any transformation, without any awkward contortions. And that is not true of any other data model that exists, that at least I know of. And if we are also able to expose that beautiful data model in an equally beautiful, dare I say, magical product surface, then I believe that the property graph model will live up to its full potential. And it can become the default, the first choice for most new software projects. So that gets us to the end of this opening keynote. And so I want to take stock of where we are and what we've said so far. But I want to start out by just reminding ourselves about that usability hierarchy from before. We start out at ground zero, right? Where if we want to build something, it's initially impossible, and then we make it possible, and then we move from 1 to 2, right? From possible to usable to normal and so on, all the way up to magical. And if we then look, we zoom all the way out and we look at our collective achievements in the previous decade. And we apply that hierarchy to the entire graph database category. We really went from 0 to 1, the way that I look at it at least, in 2010, right? In 2010 when we GA'd Neo4j 1.0. This made it possible to operate on graph data at scale in a real way, embodied in a generalized product that could be deployed into multiple use cases. And that was huge, right? A second milestone was when we incorporated Cypher into the product. And this gave us a shared language for thinking about and working with graphs. It made graphs usable from any programming language. So that was a big milestone for us here at Neo4j. But we've actually never seen our job solely as advancing Neo4j the project, Neo4j the product, or even Neo4j the company. We want to advance the entire concept of graph databases, the graph database category. We believe that the idea of that, the idea of looking at relationships in data, figuring out how things fit together, that idea is bigger than we are. And so a few years later, we grouped together with several other graph database companies, and we launched GQL, to make graphs industry normal, right? And this is the first time in the history of databases that a new query language was adopted side by side with SQL. The first time in the history of databases. So it's a milestone achievement. And it really catalyzed this broad mind share across the industry, accepting graphs as a new standard. And so that brings us to now, where we are now in October in 2020. And in so many ways, I feel like the preceding decade, and while I'm so proud of what we've all accomplished as a community, was just laying the foundation, right? The groundwork has been put in place. The idea of graphs, inception, right, in this slide, if you will. A way to talk about graphs, initially Cypher, and then an entire industry grown together around graphs. And that all gets us to normal. This decade then, the 2020s, is about making graphs magical. And how do we get there? We follow these paths forward, the 4 themes that will shape the graph database category in the decade to come. The 4 themes that we've talked about. Obviously, a shift to the cloud, which is more than a place. It's a connected approach from your laptop to your data center to the edges of the world. Developer productivity. Graphs always at your fingertips, easy to use, effortless. New audiences like graph data scientists, so that the entire world of AI is powered by relationships in data. And then finally and ultimately, to bring it all together, the property graph model, which on some level is the data supermodel that can abstract away many, if not all, of the other data models over time. For those of you who have been with the Neo4j community for a while, you've certainly seen that one of our taglines, or our motto, if you will, is graphs are everywhere. And it's the observation that graphs is, like I mentioned, an idea bigger than what we are. It exists everywhere in life. It exists in data, for sure. It exists physically in our bodies. The human brain is biologically wired as a graph with neurons connected to other neurons through synapses. If you double click and zoom all the way in on your body, those cells consist of protein networks. How things fit together in a connected data structure is something universal, right? And so we observed that by saying graphs are everywhere, right? I believe that the next decade, in the 2020 through 2030, is not graphs are everywhere, though that of course still remains true, but it really is the decades where graphs are for everyone. So that concludes this keynote. I took liberties of looking out very far. Most of the rest of this conference will be very practical and pragmatic, and it will be about the today. But I hope you enjoyed this view to the future of at least how we here internally at Neo4j look at how the category is going to evolve. There's 10 hours of amazing content ahead of you. So I hope all of you are having a fantastic time listening into the sessions. I always talk at all the conferences where I am is that we are graph people, right? And what ultimately defines us, though, if you peel away all of the cruft and all of the noise, the one thing that sets us apart compared to other communities is relationships. It's much harder to strike relationships in the virtual world than compared to the physical world. And I wish this could have been a physical event so we could meet face to face. But in lieu of that, log on to the chat areas, the lounge in big marker, tweet about this, use the Neo4j hashtag. But by and large, beyond everything, make sure that you connect. Have a fantastic day. Thank you very much.